Good everybody for today. And my name is Jiri Novotny, and I would talk about the role of hard acceleration for cybersecurity. I will not go deeply into FPGA's technique. I will don't go deeply into packet processing, but just show the role of the hardware accelerators for the security. Let's start talk about the motivation of the presentation. So we know that the world is changing quickly from the last centuries. Today, the cybersecurity is very important, and income from the cyber crime is right now higher than from drugs. What's are on the network? We see spam, phishing, social engineering, and all that stuff. We can see. We can see also botnet business and many other issues on the network today. Also, the DDoS attacks against Estonia and Georgia was in the last years very important things, and we need to prevent these activities. So for today, the internet is battlefield. There is, if we talk about the battlefield and about the war in the internet, so we need to ask some questions. Do you know what's happening on your network? Is your network really secure? Is you able to detect and work with the network incidents? Okay, when we connect our city in a year 92 into internet, we just look for basic functionality. We were very happy that we have packet coming from all the rest of the world. We were able to send emails, and it was all. Later on, we start to work with incidents, but passively waived. So it means that there was an accident, and we try to figure out what's happened on the network. Right now, we are in the situation we have tools for intrusion detection, and we can handle with the accident in real time, say not just in a time, but very close to real time. So let's talk about the main issues in present computer security. Of course, we have huge amount of data which are going through the network. We have huge amount of monitoring data as well. The software-only monitoring solutions are not fast enough. We know that, for example, Snort can run on modern computers up 500 megabits, maybe gigabit per second, but it's not fast enough for 10 gigabit lines. Of course, we have many security tools, but most of them are very complex for the configuration and the need to very skillful people which will work with. Okay, we can also use hardware appliance, but they are not flexible enough. And data from network devices, if we use, for example, routers, and we use, for example, NetFlow data from the Cisco routers, the data has no sufficient quality for the security aspects. So here are the one of possibilities. It's our vision how to protect our network, our network. So here is the operational center, which takes data from the probes which are deployed on the edges of the network. The probes are hardware acceleration monitoring center, and they send information in the security operations center. Today in my presentation, I will talk about the probes, which is commodity PC with the hardware accelerator card. So I will talk about the hardware accelerated monitoring center, HAMOC. How it looks like. The main goal of our approach is to make hardware acceleration user-friendly, because if you deploy to anybody some just card with hardware acceleration, what to do with it's that piece of metal, so it doesn't work. So we try to use to have hardware acceleration much user-friendly. The second goal is to use existing appliance, because if administrators know to work with Wireshark, with TCP/DAM, with NetFlow data, and so on, but they don't want to learn a new learn a new tools. They don't want to use something what is unknown. So they would like to use known tools. And of course, we also need to show the best practices how to use that device. So there is the architecture of our probe, of our Hammock probe. On the bottom is hardware acceleration. It's a card from the Combo V2 family. And the cards kept packets and send them in the operational system. And the operational system, it's just Linux PC and out-of-shell box, do the rest and send the necessary information to the operating center. The card has possibility also block the traffic, but right now we use just the card for the monitoring. We can let the data pass through and do some firewalling, but right now we use just the monitoring possibilities of the card. So, and on the top of the hardware, here in software, in user space, there are common tools what are very widely used. So it's NetFlow, deep packet inspections, and many others. So just we will go from the bottom of the stack up to application level. So on the bottom, there are the Combo V2 family cards. Combo cards were developed in CESNET together with Masaryk University and Brno University of Technology. And right now we have second family of the cards. The cards has a sandwich design. It's the mother card down here. It's mother card and aligned card with the interfaces. The card is equipped with Virtex 5 Xilinx, with Xilinx Virtex 5. And we use one of the biggest chips available on the market. Here we have solution for 2 10 gigabit ports. We have line cards for the 4 1 gigabit ports, and right now we have another line cards with another Virtex FPGAs with 4 10G ports. We use this card. We use also for the preliminary tests of the 40 gigabit Ethernet. The cards are manufacturing here in Czech Republic, and they are also available on the market. So, but as I said before, just hardware is that piece of material, so it doesn't work. We need some firmware which make the hardware up and running. So we have SDK. It's a system development kit for our cards, because in the first years of the project, we wrote all application, all firmware from the scratch. But later on, we found that we do still the same work. So we prepared some development kit which make firmware designers much easier. It's a set of functional blocks. It's on one side, it's input buffers, output buffers, and all necessary support for the network communication. On other side, it's DMA and very fast DMA channels and transfer into host computer. And here is the place for the algorithms or for the user application. So a developer can just prepare his firmware or just his algorithm and don't need to care about that pieces of the firmware. In Hammock Center, we use one of our firmware, which was developed with this kit. Here, in acceleration core, we built hash-based packet distribution. So here we have 2 10 gigabit interfaces and up 16 DMA channels into user space, into software. So we can simply divide the traffic among the processor cores, and so that way we can operate on much higher throughput. Because the main issue with the using of computer is the spreading data a bit among the processor cores. Nowadays processors has big issues with spreading of the data between the cores. So we talked about the hardware, we talked about the firmware. Now we will talk a little bit more about the software, which is probably picture you know. So here is the hardware with the firmware inside. Here is the Express PCI bus, and here is the packet rings in the RAM memory. We have three approaches how to connect into the packet rings. We can use either standard application over Linux TCP/IP stack. It's a slowest way, but there is most program which work with the IP stack. The most common way used in monitoring is PCAP. So we have PCAP library here. So we can use PCAP application. It's a way which still is sufficient for many applications, but it's much faster than the standard TCP/IP stack. And after that, we have straight zero copy application. It's fastest way, but the program must be tuned for that interface. So software developers can make decision if they look for slow, but slow possibilities, but convenient for many applications, or fastest possibility, but they need to tune the application. Of course, we need to configure that Centrum, so we made decision to use a netconf because it's a RFC standard, so we write as part of the diploma work from Radek Krejci. He wrote the netconf. Netconf protocol, implementation of netconf protocol, and we can use netconf for the configuration of the boxes. How to connect the HAMOC into network? There are two possibilities. There are three possibilities in fact, but the one which is not here is to use span port of the big box of the Cisco or Juniper or other, but it's we don't support this because data coming from the span port are many times there are very bad quality, very poor quality. So the one way is to use inline mode. We have two port cards, so we can use inline mode, or we can use just tap. We can use tap and use card just for the monitoring. So it's two possibilities. Some pictures about the throughput. This is the theoretical 10 gigabit speed. We achieved 10 gigabit speed for the moving packets from one port to other port, or moving data up to software in the box. So in all cases, we have 10 gigabit. Even in the software, we are limited by Express PCI bus. With theoretical throughput is 16 gigabit per second, with PCI Express time 8 generation 1, but real numbers are about 12 gigabit because there are some overhead of the PCI Express bus. So we achieved speed for transfer into software 12 gigabit per second. And here is the utilization of the processor. So it means that we have, in many cases, there is utilization less than 20% of one processor core. So let's just summarize it. The HAMOC is based on the hardware accelerators. We use netcode platform for rapid firmware development. We can, in this hammock, we use Honeyc firmware, but we can use others firmware. We have firmware for packet filtration and others. We can change filtering rule if we need to change them without packet loss, and there is several API for the upper layers. Okay, and next we will go into several use cases. The first use case, the first block of use cases is based on the deep packet inspection. It's classical approach. So first, let's talk about nanosecond timestamps. We have our combo card. We have another module for the GPS, connection to GPS, and we can send packets with nanosecond timestamps in the software. It's the timestamping are done in the hardware, so it's really timestamps. It's not like timestamps done in kernel because could be much worse situation. So it works like there is a solution. We have tab, combo card, and here we do timestamping, and we can observe them. But here, with the nanosecond, we can not use TCP-DUMP. It has not support for that, but we can use T-Shark and Wireshark. Why it is important? If we look on the results from the Wireshark, we see that 3 packets has the same timestamp. We don't know the ordering of the packet because we don't know which packet was first and which was third. So it's the standard resolution, microsecond resolution. Here is the situation with the nanosecond timestamps. We can see that we can order, we have ordered packets right here. There is a second use case. We can use remote packet capture. So there is a server, it's our hammock, and via RPC cap daemon, we can send packets to the other client, which could be either Microsoft or Linux or BSD or Apple, whatever, and we can run Wireshark remotely. So we just capture packets, filter them, and send them into other client machine for the observation. It can be convenient in some networks where the administrators use, for example, Windows tools because that our server works on the Linux. So. The next use case is voice VoIP analyzer. We do hardware filtration of the packets. For example, for voice over IP, so we filter out packets with SIP, signalization with RTP, RTCP, and other ones, and send into software. So we have 10 gigabit lines, and we know that voice over IP could be in a range of 100 of megabits, so we can filter out all the traffic without packet loss and process them without packet loss. And here is the other picture, how to make Snort more powerful. You know that Snort is very process consuming. So the speed in modern processor is 500 megabit per second, maybe gigabit per second. It depends on the rule set. So in our case, we are able to do hash-based packet distribution, and we can distribute the data among the processor cores, and each processor handle with some portion of the packets. We did some measurement, and we were able with 8 processors with distribution data to 8 processors to speed up Snort about 6 times. So there is some overhead. It's not 8 times because we used 8 processors, but 8 processor cores. So, but we had about 8 times better throughput than with just without that distribution. Okay, now I would like to go in the little bit other area, because the first use cases was based on the deep packet inspection, but you know that nowadays there could be some issues with the deep deep packet inspections. It's a huge amount of data, and there is also issues with the encrypted traffic. For encrypted traffic, deep methods based on deep packet inspection doesn't work. So we believe, like the guys from the switch, for the NetFlow monitoring. You know, the NetFlow monitoring is based on the Cisco V5, V9, or IPFix technology, and it's enabled to watch the network in real time. The previous version of our probes was developed in the frame of Giant 2. It was Giant 2 security toolset. It was Flowmon probe together with Peter Haag, NFSN. So it's a that two things are very powerful tool for the network monitoring. Just the basic principles. The flow is defined by the source and packet, source and destination IP address, source and destination port, and protocol number. We observe timestamp, number of packets, sum of bytes, TCP flags, on many other. And need to be said that flow is just one directional, so it's one flow is this and one flow is there. So it's a basic principle, and even with that functionality, we can do a lot of work for the cybersecurity. We can observe our network in real time. But as we have some hardware acceleration, and we can have more sophisticated, we can build more sophisticated tools than just a regular NetFlow. We prepare some other extension of the NetFlow monitoring. For example, here we have web access analyzer. We a little bit extend the data coming from the probes, and we have also information about the names in the web in the HTTP packets. So we can have the ordinary regular NetFlow data extended with that information, which is much better for the network administrator. Let's talk about the next use case. We developed that application just months ago because of issues with the IPv6. You know that IPv6 became to be a huge security issue on the network. For example, if you have some Vista or Windows 7 desktops, they try, every time they find firewall or something like that, they try to use IPv6, and they connect server in Microsoft and do something which you don't know what they do. So our solution, which we deployed on our probes, is to extend NetFlow monitoring to be able to observe data inside the tunnels. So we have information about the envelope, and we have the information also in the tunnelet and the tunnelet traffic. It was very interesting. We deployed it on our university network and Masaryk University in Brno. The network is a big network. We have about 40,000 students. We have about 30,000 computers on the networks and many laptops and things like that. And when we did the measurement of the IPv6 traffic on the university, we were very surprised because the regular traffic, which was regular IPv6 traffic, was 2 times less than the traffic which was spontaneous traffic from the Windows boxes. So regular IPv6 traffic were 2 times less than traffic which was unwanted in our network. And you know that there is an issue how to block that traffic. It's especially in the university environment, it's very hard, tough things to block something. So we know that it take a long time when we fix that things, when we set up firewall. But right now we have at least the possibility like to monitor the traffic. So we are like a man with one eye among the blind guys. There is another use case. Okay, we have data, we have a lot of data in our databases, and what we should do with this. We can do manual analysis, but it's time consuming and need very skillful person who are able to do some manual analysis. So as a part of the research for US Army, what we had 2 grants for US Army. We developed or tried to develop some tools based on artificial intelligence which can detect some attacks. Okay, so we talked about the deep packet inspections, we talked about the flow analysis, and now what we can do with the network defense. The first 2 set of use cases are right now deployed, and we use them in a real day life. There is the future. We can use our cards because we have 2 port cards for the packet filtering. We can filter and do firewalling, or we can send wrong packets to the other place. We can do packet sniffing, load balancing, and so on. So the first we can do packet filtering based on IP tables. It's I said that it's his future, but right now, as we are developers and we have our piece of network for our development, we test that possibility on ourselves. That hammock, which is deployed about half a year on our own development network, and our developers are on other side of the Z box. So we test our tools on ourselves, and after first issues, it works pretty nice. It's it's worked very good. Okay, and there is the other possibility. We can also limit specific traffic. We can slow down some traffic. So that approach can be very good. For example, when it's massive attack, you just let go through the firewall the trusted hosts, and the rest is slow. The rest traffic you slow down, and when you observe the source of the issues, you can let go up the rest and block the unwanted traffic. And just piece, there is the cherry on the cake. We catch Chuck Norris in our hardware acceleration box. So we can prove that even Chuck Norris could be catched by hardware acceleration box. So let's talk about the story. What's the Chuck Norris botnet is? It's a Linux malware, but there is very interesting. It's not botnet by commodity or normal computers like we know, but it's a botnet made by purely configured Linux MIPSel devices. It means homemade routers, homemade cameras, and many small boxes which you buy just out of the shelf and put that box on your home network and doesn't care about that. So how we found that botnet? The guys who deployed, Pavel Celeda from my team, who deployed our boxes on the university network, play with the boxes and try to observe network if the boxes works pretty good, and say, okay, hell, wow, in year 09, we have a lot of telnet traffic in our network. Who hell can use telnet traffic in the university network? So he start to check the traffic, and we start to observe what's happening on the network and what's the traffic, what's the communication is. We use the other feature of our boxes. We could filter out that traffic with some parameters, so we can filter out telnet traffic and do the inspection. What's happened. So after that, we found that that telnet traffic is it was attempt to telnet to some devices. Why we to some small home routers? So okay, we saw that. So we say, okay, let's know let's know more about that. We took several home routers, put it on the university network, and let them infect. So we use a honeypot approach, and after that we did the re-engineering. So we have samples of the code in our boxes, and we can do work with. And Pavel was also very successful because in the infected boxes, the first activity was the stopped telnet configuration from the network, and the boxes were controlled just by the IRC control centrum. So, but he found one of the boxes has a bug in the firmware, and the botnet software or malware doesn't work properly and didn't stop the traffic, telnet traffic in the box. So we were able to connect to the box and also take the data from that box. Need to be said that in that case, okay. So, sorry. Why the name of botnet is Chuck Norris? In the firmware of the malware was written Kilato in nome di Chuck Norris. So we named that botnet Chuck Norris botnet. We need to say that the infected boxes were infected just in their RAM memory. So there is very simple fixing. You just switch it off. What was very interesting with this botnet, we spent about 160 messages to ISP providers all over the Czech Republic. We had some publication in Word news, but there was not any much response. So you can see what is the security in the real life. We found a very interesting botnet, and nobody cared about that. People doesn't care about the security. It was set in the previous presentation. So here is the attackers in the time. So in 1st May we have 40,000 attacks. Here is the second is unique attackers. So you can see that our network was attacked. Almost every attack was done with other attackers. And here is the activity in the time. We discovered the botnet. Here we played the game with reverse engineering and so on. Up here we did somewhere here we did notification and botnet shutdown. We know the name of the IRC server which controlled the botnet. We contact the guys from them, no response from them. But we know that they stopped the activities. It's probably hidden right now, but we are sure that the botnet is still here and wait for other maybe more sophisticated attacks. And it was we were very disappointed because we found something and nobody cares about that things. Who was the victim? The victim was also written in the firmware. We need some just very stupid, it was a little bit encrypted, but just very stupid way, so it was not an issue to correct it. It was Telefonica Peru, and then also Telefonica Spain was on the list. Deutsche Telekom was somewhere here in that part. So, okay, conclusion. Hardware acceleration enable reliable wide-speed traffic processing even in worst-case scenarios, so we are able really process every packet on the network. We build simple development, or prepare simple development of new application. As we use flow, mostly we use flow analysis, so we can work on encrypted and tunneled traffic. The Hammock is deployed on the Cessna network, also on the network of the Masaryk University and Brno University of Technology. And the results, some results of my speak was transferred into spin-off company. I said that cards are available on the market. They are available on the market. As well, Hammock is available. Okay, future work, we would like to extend portfolio of Hammock application. As you saw, we can run standard Linux application, but time to time there is the issue and something must be tuned. But we had almost no problems to use almost all your Linux application. Next year we will start to work on 40/100 gigabit Ethernet to be ahead of the community. And we would like to deploy Hammock to more partners. The very important message, we are looking for new research and development partners. We are open for the communication. We have a big team. The research was done on the CESNet together with Masaryk University and Brno University Technology. And right now, team has about 60 members, and most of them are students from the undergraduate up to PhD students, like Radek is one of the PhD students working on the project. The team is divided into several groups, like this. That's all. Thank you very much for your attention, and if there are some questions, I will be happy to answer them.
Yes, if there are questions, please wait for me carrying the microphone to you. Are there any questions? Then I had a question. Were there any? No. A question concerning PCAP. Do you do the filtering of PCAP in the hardware, meaning compiling the PCAP filtering rules down to the FPGA?
We have one of our design, which I said that the firmware is flexible, so you can download new firmware in the hardware. The time for the change the firmware in the hardware is in seconds, so we can change the behavior of the hardware in second. And here I talked that we use the firmware for the packet distribution, but we have also firmware for the packet filtration. It's a NIFIC firmware, and that firmware allowed to filter out, and we use TCP dump, modified TCP dump rules. So we have you write your rules with the language very close to TCP dump, and you compile that rules into hardware and download the rules in the hardware. So in effect, in the NIFIC, there is two-step configuration. First is download NIFIC in the hardware, and second, download the rule in that NIFIC. So the rules are in the memory, in the card. So I talked about the packet loss change of filtering rule. So we can change the filtering rules inside the hardware without the packet loss. It was, you know, that the devices could be very interesting for some organization. And they would like to don't lose any packet when the rules are changing.
Second question, very related. Can you do the same for IP table rules so that you are effectively processing IP table rules in hardware? Or?
Yeah, we in that use case we use it's based on the IP tables. So yes, we are able to convert IP table rules down into hardware. It we use on our network.
So what are some of the challenges you see into deploying the solution to be more widespread? Is it really the problem only about speed of how fast you process the packets? Or maybe we just don't have very good algorithms to efficiently analyze the packets and discard most of them?
You know, in real life, if you want to do this work, you need a rack of computers. We have just one box with one computer, and we are fast enough. The main issue of that approach is price. It's price of the card. So we have no issue with the speed. It's wire speed solution. In the next generation card, we will go in the Express PCI generation 2, so we can go up 20 gigabit per second. We have a hardware prefiltration, so you can, for example, if you have your hammock here, so, sorry, I need to go there. Okay, in the first picture. So, for example, you can run on the same box NetFlow. You can observe a whole your network with some hardware acceleration. And here you can, if there is some attack, some issue, you can start some deep packet inspection analysis. So it's flexible. Just one issue is the price of the card. Just one issue.
In what price range is it?
I'm not business guy
Okay,
now here, but it's more than 10,000 euro.
Yeah, I expect that because you're using the big FPGAs.
Yeah, and but you need to know that you have one solution, you have one box. You don't need to have a rack of the boxes. So if you compare the approach, and it's wire speed solution, and you can just make a decision what firmware you download in the card and what application you wouldn't run on top of that.